All right, everyone, welcome back to the land of Chem. I'm your host and the author. My name is Jeffrey Drum. Thank you all so much for joining me again.
All right, everyone, welcome back. Now, today, an absolutely massive research episode presenting on-site expedition footage, chemical analysis data, mathematical calculations, and animations demonstrating all of the mechanisms of operation and chemical reactions involved in the function of the Red Pyramid of Dashur. Ladies and gentlemen, as always, thank you all so much for the support. I think that's it for today's intro. So without further ado, let's get right to it. All right, everyone, here we go with tonight's episode.
Now, to begin, in episode 66, I presented the first two components of the Red Pyramid coating compound. And you may have noticed that during the past few videos, I have been referring to previous research material that is absolutely critical to understand as we move forward in the discussion regarding the function of the Egyptian pyramids. And if you're a new viewer or a long-term subscriber, it is important to get caught up on this information as I will continue to build on concepts that have already been presented and explained. So I will be putting links to all of the referenced episodes in the video description below. And episode 66 is a personal favorite of mine as it not only covers the preliminary data regarding the chemical composition of the Red Pyramid coating, but it also explains the spectacular functional properties of a beautiful blue compound known as Egyptian blue. This is a must-watch episode presenting the foundation research that will be expanded upon in today's episode. And in that video, I explained how the silicon dioxide and sulfur trioxide components of the Red Pyramid coating worked as a copolymer that was, quote, insoluble and resistant to acids and solvents, providing, quote again, broad protection from corrosion and solvents. The coating was also repairable, with surface scratches removed through the application of heat. In this way, the coating is protective against acids and solvents and repairable when damaged. This silicon dioxide and sulfur trioxide coating compound was not only chemical corrosion resistant, but also self-repairing. But that's not the only component of this complex alchemical material. And I'll put in a quick clip now from Sunday Site Visit 71, also linked in the video description below, so you can see this red coating material up close for yourself.
And so now we're going to take a look at the coating compound that was discovered on some of the remaining casing stones that once covered the exterior of the Red Pyramid, as presented in episode 66, were the pyramids painted. And we have a chemical composition analysis of this material from samples that were taken by my colleagues at the Osiris project. And we're going to take a look at this red coating compound now. And as I just mentioned, this will be a topic for an upcoming research-based episode. So here, this is a piece of casing stone. And you can see the perfectly flat, finished surface. And if you look closely here, you can see the coating compound. This layer here and this reddish material covering the surface of the block. And you can see the line here where it was applied over the edge of the block. This would have been the exterior surface of the pyramid, and it was applied to the block before the block was set in place. This would have been another block sitting on top. So you can see it's been applied over the edge. Again, the coating compound has a slightly reddish color and a very rough texture. Here you can see another piece. Coated with that same material. And I'm going to walk around this area and show you a few other flat surfaces of casing stone here that were coated with this reddish coating compound. You can see it here on this piece. It's a red paint. Here you can see the foundations of the original temple structure. Here's the mud brick, and this is original foundation of the temple that was here first. Here's another good view in the sunlight so you can see the color of the compound. And there are several pieces here that all show traces of this red coating compound. And samples of this compound were taken from several in situ blocks on the casing stone. And I presented all of the sample locations in episode 66, where the samples were taken from the surface of these casing stones and samples from these blocks here. And chemical analysis was performed, revealing that this coating compound is a mixture of 3 primary ingredients: silicon dioxide, sulfur trioxide, and aluminum trioxide. So it appears that the red pyramid of Dashur may have been painted red. And this compound is remarkable for several different reasons. First, it contains solid sulfur trioxide. And for any of you that have been following my work, know that sulfur trioxide is one of the intermediary products of the Great Pyramid of Giza. Within that structure, in its gaseous phase, but here we see sulfur trioxide in its solid form. We also have silicon dioxide and aluminum trioxide. And you can see here what is said to be the replica capstone. And they have pieces of the original casing stone that are set into this concrete mold. And you can see here that there's a few edge pieces. There's an edge piece here. And if you look, you can see this red coating compound is on these casing stones as well. And in episode 66, I compared this silicon and sulfur copolymer to a modern coating compound that is made of sulfur trioxide and a compound known as dicyclopentadiene. You can see here the layer of the coating compound that is applied to these casing stones, the same red compound. And this modern coating compound has a number of unique properties, including corrosion resistance, specifically in regard to solvents and acids. And second, it is a self-repairing coating compound that if cracks form in the material, the application of heat will repair those cracks. A self-repairing, chemical corrosion resistant coating compound. And all of those applications should be sounding very, very relevant to the topic at hand. All right, and I'm glad we came around here, because check this piece out. Here's a corner piece of casing stone. So we're here on the southwestern corner, and look at this one. A beautiful piece of casing stone right here. Check this out. Again, this is an edge piece. You can see the flat surface here, the paint on this side, and you can see the red coating compound. Looks like this is actually an edge piece, like one of the corner pieces that would have gone here on the edge. It looks like an edge piece because there's, again, you can see traces of it here that would have coated this whole side and this whole side. And remember, we're looking at a compound. Sulfur trioxide, silicon dioxide, and aluminum trioxide. This is a beautiful piece.
All right, now that you've seen the coating, let's proceed with evaluating the remainder of the chemical constituents that you can see here in the analysis data that was conducted in conjunction with my colleagues at the Osiris project from samples of this material that were taken back in 2010. And I will start with eliminating what may be naturally occurring components of the limestone substrate itself that are not present in all of the samples, including magnesium oxide at a maximum of 3.32%, potassium oxide at a maximum of 3.47%, titanium oxide in only one sample with 0.4%, and iron oxide maximum 2.21%. And the irregularity of the concentration and inconsistency in its inclusion in the sample analysis suggests that these are naturally occurring and not representative of the coating material itself. But here we have the purest sample of just the coating material itself, with 40.98% solid sulfur trioxide, 28.88% silicon dioxide, and the component that I intentionally excluded from episode 66 is the 20.81% aluminum trioxide. And I was saving the discussion of this compound as at the time episode 66 was released, I had not yet revealed the power source of the Egyptian pyramids, lightning, as presented in episode 106. Again, if you are a new viewer, it is critical to go back and watch these episodes that are linked in the video description below, as up until now, we have been doing Chemistry 101. And there is a good reason that I entitled my first book, An Initiation into Ancient Chemistry, as it presents the basics regarding the function of the Egyptian pyramids. But now that the foundation mechanisms of operation have been established, I will be moving forward into the advanced physics and chemistry processes, reactions, compounds, and applications, and the utilization of aluminum trioxide in this coating compound as related to its electrical and chemical properties is a perfect example of where my research will now progress into far more complex topics involving lightning, electric field chemistry, and a whole lot more. So let's start with an evaluation of the aluminum trioxide molecule and its properties. And I will quote the following here, this one coming from aluminummanufacturers.org. Aluminum oxide is a common, naturally occurring compound that's employed in various industries, most particularly in the production of aluminum. The compound is used in the production of industrial ceramics. Its most common crystalline form, corundum, has several gem quality variants as well. The chemical properties. There are many different forms of aluminum oxide, including both crystalline and non-crystalline forms. The chemical formula for aluminum oxide is aluminum 2 oxygen 3. It is an electrical insulator, which means it doesn't conduct electricity. And it also has relatively high thermal conductivity. In addition, in its crystalline form, corundum, its hardness makes it suitable as an abrasive. The high melting point of aluminum oxide makes it a good refractory material for lining high temperature appliances like kilns, furnaces, incinerators, reactors of various sorts, and crucibles. Use in the production of aluminum. Most common use of aluminum oxide is the production of metal aluminum. Metallic aluminum is reactive with oxygen, which could cause corrosion to build up. However, when aluminum bonds with oxygen to form aluminum oxide, it creates a thin coating that protects it from oxidation. This keeps the aluminum from corroding and losing strength. The thickness and other properties of the oxide layer can be changed using the anodizing process. Aluminum oxide is also a product of the aluminum smelting process. Now onto corundum gemstones. The most common crystalline form of aluminum oxide is corundum. Both rubies and sapphires are gem quality forms of corundum. They owe their distinctive coloring to trace impurities. Rubies get their deep red color and laser qualities from traces of chromium. Sapphires come in a variety of colors, which come from other impurities like iron and titanium. The hardness of different kinds of corundum makes them suitable for use as abrasives and as components in cutting tools. Now, to those of you that have been following closely, this should be sounding very familiar, as aluminum trioxide, corundum, and abrasives first made their appearance here back in episode 53, a metallurgical analysis of ancient Egyptian saw blades, another critical video linked in the video description below, which presented numerous studies featuring chemical analysis data from saw blade cuts in stones across ancient Egyptian sites, including this article from the Metropolitan Museum examining the material discovered in this tubular drill core into a limestone block. And I will quote here, "This is an X-ray elemental map showing the distribution of aluminum, silicon, and calcium in the abrasive sample. The yellow particles are corundum fragments. The presence of abundant corundum particles conveys high abrasive efficiency to this material and strongly suggests that this mixture was deliberately used in the drilling process of the hard limestone fragment. Remains at the bottom of the drill hole thus consist of a mixture of the abrasive, the powdered limestone, and corroded fragments of the bronze drilling tool. Altogether, these findings suggest the use of a bronze tubular drill in conjunction with a corundum-rich abrasive mixture." So the metal blade itself was not pure copper. This is a massive myth perpetuated within the, quote, lost ancient high technology community, but rather an alloy of copper and arsenic known as arsenical bronze. This alloy completely changes the property of the metal, producing an extremely capable metal blade. But the blade itself is not the most important detail, as the magic of ancient stone cutting technology is all about the abrasives. And I will continue quoting from the same article here. The ancient Egyptian craftsmen were exceptionally skilled and prolific in extracting and shaping a wide variety of stones. For millennia, soft and hard stones were quarried, cut, drilled, carved, and polished using a variety of tools and techniques. And it is generally agreed that abrasives played a significant role. Scientific analysis using scanning electron microscopy and energy dispersive X-ray spectroscopy identified the material as a mixture of predominant angular grains of corundum with jagged edges and a few other minerals such as quartz, rutile, feldspar, apatite, ilmenite, augite, biotite, and chromite, usually smaller in size and with high angularity. Very fine particles of calcite surrounded the bigger particles, which are most likely the remains of the indurated limestone that has been drilled. Several particles of corroded bronze and green copper corrosion products are dispersed among the above-mentioned particles, imparting the light green color. So we know that aluminum trioxide was being utilized by this ancient civilization for various applications, including in abrasive slurries for stonework. But what was its function in the red pyramid coating compound? I will continue quoting here regarding the uses of aluminum trioxide in ceramics. Aluminum oxide, also called alumina, is used in engineering ceramics. It is hard and wear resistant, resists attacks by both acid and alkali substances, has high strength and stiffness, and has good thermal conductivity, which makes it valuable in manufacturing a variety of different ceramic products. These include things like high temperature electrical and voltage insulators, instrumentation parts for thermal test machines, seal rings, gas laser tubes, and other laboratory equipment. Okay, now we're talking. Introducing properties that are directly related to the topic at hand regarding the function of the red pyramid as a chemical manufacturing structure. But let's keep evaluating these applications. This coming from the Physics Fact Book, and I will quote here, aluminum oxide is an electrically insulating material with high resistivity that increases with purity. With its high corrosion resistance, it does not wear easily, even against strong acid. Since aluminum oxide covers all aluminum metal, it is responsible for the metal's resistance to weathering. A thin layer of alumina will form on any exposed aluminum surface and protects it from further oxidation. Diamond tools are needed to machine or grind alumina. Thus, this material is typically used for high temperature electrical insulators, high voltage insulators, electronic substrates, thermometry sensors, and grinding media. It is also used for gas laser tubes, furnace liner tubes, abrasion resistant tube, elbow liners, laboratory instrument tubes, and sample holders. It is an excellent material for the use of engineers and scientists.
So you do have a plan? Yeah, Mr. White. Yes, science. Okay.
Hell yeah. The science of ancient chemistry for high temperature electrical insulators and high voltage insulators. Now we are really getting somewhere. And to quickly summarize the properties of aluminum trioxide and its function within the red pyramid coating compound that also included the silicon dioxide and sulfur trioxide copolymer. Quote here, it is hard and wear resistant. It has excellent dielectric properties from DC to gigahertz frequencies. Resists strong acid and alkali attack even at elevated temperatures. Good thermal conductivity and is typically used in high temperature electrical insulators, high voltage insulators, and electronic substrates. Aluminum trioxide, also known as alumina, is an electrical insulator with the following properties: a dielectric constant higher than silicon dioxide, the band gap higher than silicon dioxide. It also has many applications, including electrical insulators used in power electronics, high voltage, high frequency insulators used in high temperature applications, heating element supports used in high temperature applications, and it also has other properties including high corrosion and wear resistance, making it the perfect material for an ammonia solution chemical manufacturing pyramid that was powered by lightning, ensuring that the electrical current was contained within the structure itself to be utilized in the electric field chemical reactions inside the internal chamber system. And remember, ladies and gentlemen, that the red pyramid isn't the only structure that was coated with a sophisticated chemical compound. Go back and watch episode 83 regarding the coating compound discovered on the central pyramid of Giza that you can see here on some of the remaining casing blocks surrounding the structure that was first evaluated again by my teammates at the Osiris project, who have granted me exclusive access to all of this chemical analysis data. And this coating compound contains a similar chemical composition to that of the red pyramid, with the addition of an exterior application of a phosphate layer. I'm not going to go into great detail on that now. You need to go back and watch episode 83 for a full explanation. But what I will say is that now we have the chemical analysis data, and we know what these materials were made from. And with some experimentation, it may be possible to reverse engineer the manufacturing process that was used to create them, which still remains a mystery for now. And it would be hypothetically possible to cook up a batch of this incredibly sophisticated and functional chemical compound to see what it was truly capable of. And this, ladies and gentlemen, is just the tip of the iceberg, what you can expect here on the Land of Chem in 2025.
In episode 141 and episode 142, I explained the genesis of ancient lightning technology and described how it was implemented through stone circle and standing stone obelisk systems to bring rain and atmospheric nitrate fertilizers to specific agricultural areas for the fertilization of both hunting-gathering forests and proto-domesticated farming land. And I am proposing that the knowledge and understanding of these lightning-powered atmospheric chemical reactions is the origin of the Egyptian pyramids that were designed to capture lightning in a bottle, or rather, capture and containing lightning within a chemical reactor chamber, with lightning providing the power source for the chemical reactions in the same way as it did with the atmosphere surrounding the ancient stone circle systems, but now capturing that energy within the pyramid chamber systems to drive a variety of different mechanisms of operation and unique chemical reactions within each structure. And ladies and gentlemen, as I mentioned before, what we will be discussing in 2025 is no longer just Chemistry 101, but something far more complex and absolutely genius implementation of the forces of nature in a way that I could have never anticipated. So now let's go back to episode 108, Electric Fields Inside the Great Pyramid, where I presented a fascinating research paper entitled, Study Reveals the Great Pyramid of Giza Can Focus Electromagnetic Energy, that demonstrated the capability of the Great Pyramid to concentrate both magnetic and electric fields, specifically in the area surrounding the so-called King's Chamber and Antechamber, otherwise known here as the sulfur furnace and acoustic catalyst chamber, which is direct confirmation of the capacity I just proposed for the pyramid design being implemented to intentionally direct, contain, and sustain electromagnetic fields induced from lightning strikes to facilitate various mechanisms of operation that drove chemical reactions within each structure. And in episode 117, I introduced the topic of electric field chemistry, literally capturing lightning in a chemical reaction bottle. And I will quote here regarding electric fields in chemistry: exploring the fascinating world of electric fields in chemistry offers a deeper understanding of how atoms and molecules interact with each other. Electric fields permeate our physical world and play a pivotal role in chemical bonding and reactions. And I presented several research papers explaining how electric fields can be utilized in a variety of chemical manufacturing processes. Best summarized in this paper here, Electric Field Intensified Chemical Processes and Reaction Chemistry, stating here, electric fields represent an important resource that can be utilized for process intensification in the chemical industry. Utilization of electric fields provides an efficient and cost-effective way for intensified chemical processing and reaction chemistry. And in episode 120, I explained how the ability of the Great Pyramid to concentrate electric fields around the acoustic catalyst chamber that was experimentally proven in that research paper was implemented to induce electric fields within the quartz-embedded red granite, thus activating the inverse piezoelectric effect to generate ultrasound, which catalyzed the conversion of sulfur dioxide into sulfur trioxide within the acoustic catalyst chamber, and the oxidation reaction via acoustic cavitation of the intermediary sulfurous acid into sulfuric acid within the contact process chamber. Again, within each pyramid, these electric fields were utilized using different materials to activate a variety of mechanisms of operation within each structure to produce unique chemical reactions. In the case of the Great Pyramid, using electric fields to induce the inverse piezoelectric effect within the granite to produce ultrasound, which catalyzed the reactions to produce sulfuric acid within those respective chambers. So now, let's turn our attention to perhaps my favorite Egyptian pyramid, the structure where the land of Chem was born.
All right, everyone. I hope you're enjoying the video. And please remember to subscribe for more content if you're interested in the technology of ancient civilizations utilizing physics and chemistry and the function of the Egyptian pyramids and other ancient structures from around the world. If you want to help support the channel, you can pick up a copy of the Land of Chem book and grab some merch at thelandofchem.com and for access to exclusive content. Subscribe to the members-only channel now with 19 massive research episodes revealing some of my most groundbreaking discoveries thus far. Links to everything in the video description below. Thank you all so much for the support. Now, back to the video.
The Red Pyramid of Dashur. And let's see if this concept of electric field chemistry has any applications here. In the synthesis within its chambers for the production of aqueous ammonia. In my opinion, the Red Pyramid, the first major Egyptian pyramid with sophisticated reaction chambers, was literally designed to harness the energy of lightning to internalize the exact same atmospheric chemical reactions that provided fertilizers for the ancient Neolithic stone circle building civilizations, effectively capturing lightning in a bottle and strategically utilizing that energy within contained reaction chambers, specifically the final synthesis chamber that you can see here, to create water-soluble nitrate fertilizers, i.e. aqueous ammonia. And ladies and gentlemen, what you are about to see may be one of my most significant research discoveries, revealing the true brilliance and capabilities of these ancient pyramid chemical reaction chambers, as this electric field chemistry was implemented to eliminate the need for high temperature ammonia synthesis. And with the greatest pleasure, I finally bring you this article here entitled Elucidation of the Role of Electric Field on Low Temperature Ammonia Synthesis Using Isotopes. And I will quote here the highlights. Electric field brings high yield on low temperature catalytic ammonia synthesis. And furthermore, here from the abstract, we have found that an electric field brings high yield on low temperature catalytic ammonia synthesis over a strontium-based catalyst. Results show that the electric field promotes proton hopping on the catalyst surface, and it brings a change in the reaction mechanism from the conventional one to the N2H intermediate mechanism. In the electric field, N2H intermediate plays an important role, enabling low temperature ammonia synthesis. And here is a diagram showing how these electric fields drive the synthesis reaction of hydrogen and nitrogen to create the N2H intermediate over a strontium-based catalyst, a reaction that produces the final ammonia product. And for those of you that have been paying attention, the mention of a strontium catalyst should be blowing your mind right now. And for those of you that don't realize the colossal importance of this detail yet, let's just take a little walk down memory lane to some videos from almost 2 years ago that any new viewers can now find in the chemical analysis data playlist, episode 36, episode 55, and episode 68, chemical analysis of the red pyramid staining, parts 1, 2, and 3. And what did we find in these samples from the mysterious staining emanating from the walls of the red pyramid's reaction chambers? This bizarre crystalline material. Well, of the 39 different elements discovered in these samples, the highest concentration of metals were both iron and, drumroll, strontium, with iron being the catalyst predominantly used in the modern Haber process for the production of ammonia, and the novel strontium-based catalyst being implemented for the low-temperature ammonia synthesis reactions. And the truth shall set you free. And here you can see a sample with concentration of 57.87% iron, and the concentration of strontium coming in at hundreds of times higher than any of the other metals discovered in the sample analysis. And I would propose that the Red Pyramid, just like its counterpart in the Great Pyramid, has the same capability to concentrate both electric and magnetic fields in specific areas throughout the pyramid. In this case, focusing the electromagnetic fields around the final synthesis chamber, which may explain its unique orientation within the structure. All right, now, I'm not quite finished yet. Let me hit you with one more before I drop the mic on this episode. Now, what do we have here? And I will quote once again from this article: electromagnetic field enables ammonia synthesis at low temperature. Stating here, ammonia, one of the most ubiquitous industrial chemicals, is required to manufacture nitrogenous fertilizer and can potentially be a next generation green fuel. The reaction of fossil fuel derived hydrogen and nitrogen, i.e., the Haber-Bosch process, under high temperatures, approximately 500 degrees Celsius, and high pressure, above 15 MPa, uses 2% of the global power and emits almost 1.5% of global greenhouse gases. However, they state here that using commercial iron-based catalysts, the Tianjin University team devised an electromagnetic field-assisted Haber-Bosch method for ammonia synthesis under moderate circumstances. With the electromagnetic field aid, the onset temperature is 100 degrees Celsius, which is obviously lower than the onset temperature without EMF support of 300 degrees Celsius. So, ladies and gentlemen, by implementing electric fields into their chemical reactions, the builders of the Egyptian pyramids were not only able to synthesize sulfuric acid by using sound within the Great Pyramid, they were able to drastically lower the operating temperatures required for synthesizing ammonia within the Red Pyramid of Dashur. And this is just the beginning. The Egyptian pyramid chemical manufacturing sequence is initiated at the Step Pyramid of Saqqara, and the natural gas extraction operations that were presented in episode 125. Methane is not only a valuable fuel, but also a critical primary source of hydrogen utilized in industrial chemical synthesis reactions, specifically in this case, within the Red Pyramid of Dashur, a structure that was designed with a series of internal chemical reaction chambers, the end product of which is an aqueous ammonia solution, ammonia gas dissolved into water. And although the process itself has a strong resemblance to our modern-day Haber process, there is a significant difference in the product, where today we manufacture liquid ammonia, ammonia gas supercooled until it condenses into a liquid form, whereas the ancient process product is aqueous ammonia, again, ammonia gas dissolved into water, a crucial detail that will be relevant when we reach our discussion on the mechanisms of operation within the final synthesis chamber. Now, if you take a look at this comparison between the first apparatus created by Fritz Haber for synthesizing ammonia and the configuration of the three chambers within the Red Pyramid, his inspiration becomes crystal clear. And it is a known fact that Fritz Haber was fond of vacationing in Egypt and did so numerous times throughout his life. And this industrial scale ammonia synthesis reactor project, developed in the early 1900s, was bankrolled by an Egyptian financier. And I believe that by reverse engineering the Red Pyramid, the same way that I have, old Fritz Haber discovered the ancient industrial chemical manufacturing system that I am about to describe today, which, as I have proposed in episode 142, this ancient ammonia pyramid chemistry technology has its genesis in lightning. Attempting to literally catch lightning in a bottle by creating reaction chambers that can turn nitrogen from the air into ammonia, the most important agricultural fertilizer that has ever been created. And the process that Haber developed in conjunction with Carl Bosch implements a series of reactions that begin with methane as the primary reactant and the source of the hydrogen syngas that is combined with atmospheric nitrogen from the air in the final synthesis chamber. The exact same sequence that I have determined was occurring within the three chambers of the Red Pyramid. And don't forget, as discussed in episode 72, Alchemical Symbolism of Ancient Egypt, Part 1, that the etymology for our modern word for ammonia traces directly back to ancient Egypt and the deity Amun, who, of course, is the god of fertility. And you can see the two sheaves of agricultural material growing out of his crown here, an esoteric symbol for the knowledge of the gods, ancient industrial chemistry, and the synthesis of ammonia-based fertilizers. Now, let's examine the primary steam reformer and the series of mechanisms of operation that drive the chemical reactions occurring therein, which convert methane and water into hydrogen and carbon monoxide, starting with the methane inlet located in the northwestern corner of the primary steam reformer that I have documented on numerous site visits into the Red Pyramid, including the upflow staining directly above the methane inlet, indicating its function to introduce natural gas into the reaction chamber. Next, stage 1, filling the chamber with water. So here you can see some very old photos from inside the Red Pyramid showing a variety of details that will be discussed in this series. For now, let's focus on the staining formations that are found in the lower rectangular portion of the chamber. This crashing, wave-like pattern that is found in the southeastern corner of the primary steam reformer that flows around the bottom of the chamber before crashing back up into the northwestern corner. These fluid dynamics were demonstrated in episode 70, Red Pyramid Fluid Dynamics Modeling Series Part 2, and the communication encoded in the Egyptian pyramids, where we simulated the water injection process coming from the inlet shaft located at the bottom of the northern pump shaft in a container with the same proportions as the lower rectangular section of the Red Pyramid primary steam reformer. And this still unexcavated inlet shaft is shown on the diagram here. Now, remember these two crashing wave-like formations, as you will see the exact same pattern revealing itself in these fluid dynamic modeling demonstrations. Check this out. All right, now that the initial water filling process has been demonstrated, the next basic mechanism of operation is raising the water level to compress the methane gas into the upper vault. In this closed system within the primary steam reformer, this will increase both temperature and pressure within the reaction space. And in episode 48, the basic physics involved in this step were also demonstrated. And I'll put in a few clips now from that episode so you can see the system and these basic principles in operation. And note the pressure gauge and markings in the first video, which will indicate the pressure increase inside of the container. Check this out. huge thank you to friend of the channel John Sage for his work on the inlet shaft and these fluid dynamics models. It was really cool to see this system come to life, and we may have more in store in the near future. So now that the fundamental principles have been demonstrated, let's put it all together, and I will walk you through, step by step, all of the mechanisms driving the chemical reactions within the primary steam reformer. Now, for reference, this is by far the most accurate diagram that I have found showing the exact configuration of the red pyramid reaction chambers, with the northern pump shaft here, the water inlet here, the primary steam reformer, the secondary air reformer, the drain shaft, and the final synthesis chamber. And for now, we are going to exclude the operation of the northern pump shaft, as there is some special magic happening in this component that will be a topic for a future video in this series. So now, for illustration purposes, I'll be using this diagram to show exactly how the system works, starting with the methane inlet. So step 1 is to fill the chamber with water until the connecting shaft between the first two reformers has been filled. This isolates the space within the primary steam reformer, and it sets the initial pressure and temperature conditions within the chamber. This will be important for some calculations that will be coming up in part 2. Next, the methane fill process is initiated, and the methane gas, which is lighter than air, will rise up, flowing into the upper reaction vault. The process continues until the reactor is filled with methane gas. And the next step will begin, further increasing the water level inside the chamber, which will begin to compress the water-insoluble methane gas into the upper reaction vault, gradually increasing both pressure and temperature. The process continues, utilizing the water to compress the methane further into the reaction vault like a plunger pushing up on the gas, further increasing the temperature and pressure within the system. The water level is raised until it has reached the 7th tier in the vault. This feature will be explained in a future episode, and the reaction between the methane gas and water producing hydrogen and carbon monoxide will proceed. Now, let me run through all of these steps without narration so you can watch the process in action. All right, now, let me introduce a few terms that are important regarding both the physics and chemistry within the primary steam reformer. First, adiabatic compression. Adiabatic refers to a process in which no heat is transferred into or out of a system, and the change in internal energy is only done by work. In our case, regarding the function of the red pyramid, the water compressing the methane gas into the upper reaction vault. Most processes in thermodynamics are diabatic, which means they transfer heat. The A at the start of the word adiabatic means without, so adiabatic means no heat transfer. Often, adiabatic processes are accomplished in an insulated container where the process happens too quickly for heat to be transferred. Furthermore, for an adiabatic compression, decreasing the volume of the system, like a piston, the temperature must increase. This is specifically relevant in the case of the red pyramid, where within these limestone chambers, there will be minimal dissipation of heat during the reaction sequence. Limestone has exceptional heat-resistant properties, where, in contrast, black basalt, for example, will absorb and maintain heat. So in this stage, there is no heat exchange. Thus, adiabatic compression occurs. If you compress a gas in a closed system without allowing heat to escape, an adiabatic process, increasing pressure will increase temperature. This happens because work is done on the gas raising its internal energy. For example, compressing air adiabatically in a piston will heat it up. So this increase of both temperature and pressure are the basic physics mechanisms of operation that drive the chemistry inside of the primary steam reformer. The conversion of methane and water into hydrogen and carbon monoxide. But, as always, this is just the tip of the iceberg, the Physics and Chemistry 101. And in the next episode, I will be addressing a few interesting articles and their implications for the function of the Red Pyramid primary steam reformer. And for those of you that have been paying attention, of course, they involve both catalysts and electric fields. This one here, scale up studies on electrically driven steam methane reformings. This work is devoted to scale up parametric studies of a new reactor for the steam reforming of methane driven by electrical current. The main distinguishing feature of this type of reactor is the use of direct electrical current flowing through metal particles to heat the whole reactor volume. Electrical current flowing through metal particles, you say? Seems like we may have discovered dozens of various types of metal particles in the Red Pyramid chemical analysis data. But there's more. This article, Improving Nickel Catalysts Using Electric Fields, a DFT, an experimental study of the methane steam reforming reaction. Stating here in the abstract, this work demonstrates the benefits of applying an external electric field to the methane steam reforming reaction in order to tune the catalytic activity of nickel. Through combined DFT calculations and experimental work, we present evidence for the usefulness of an electric field in improving the efficiency of current methane steam reforming processes, namely by reducing coke formation and lowering the overall temperature requirements. Oh, nickel catalysts, huh? Well, guess what we also found in the Red Pyramid chemical analysis data? Nickel. So like I said at the beginning of the episode, this series will be the most comprehensive, in-depth, and extensive evaluation of the physics and chemistry-based mechanisms of operation that are involved in every single chamber of the Egyptian pyramids. I will be working through all of these systems and chambers, one by one, revealing details that are going to blow the roof off of these structures, with the Red Pyramid being the smoking gun of ancient pyramid chemical engineering technology. So in the next episode, we are going to continue with the primary steam reformer, introducing electric field catalyst chemistry, and some calculations revealing both the temperature and pressure capabilities of this system, driving reactions into the secondary air reformer. And later in the series, the final synthesis chamber and a special episode on the northern pump shaft and external reservoir. Then we will move on to the bent pyramid. And if you're new to the channel and your mind is completely blown by all of this information, I highly recommend getting caught up by watching the Red Pyramid playlist so you can be up to speed on all of this data as we move forward in the series. And if you haven't already, please subscribe so you don't miss out on what will prove to be the most important research videos that I have ever produced. Before we proceed with this mathematical analysis, revealing the physics-based reaction chamber conditions inside the Red Pyramid's primary steam reformer, as I was preparing for this episode today, I stumbled across this article by Alexandre Kasyanchuk entitled "The Egyptian Pyramids Start Making Sense," discussing my work. And Kasyanchuk is a PhD in both physics and mathematics. And this article specifically focuses on extolling the virtues of my research on the Red Pyramid. And I will quote here, "I came across a remarkable explanation from Jeffrey Drum on YouTube of the Egyptian pyramid's purpose. He nailed it. In short, each pyramid was a chemical plant, with various pyramids producing various chemicals. For example, he suggests that the Red Pyramid was built as a plant that produced ammonia from methane and nitrogen." Next, he also corroborates my hypothesis on the function of the step pyramid, stating here that Drum compares the chambers in the Red Pyramid and in Fritz Haber's process, provides chemical analysis of the residues in those chambers, discusses pressure and temperature conditions for the chemical processes. Pyramids retain gases and water in tunnels and chambers under high hydraulic pressure needed for chemical reactions. And he suggests that the main source of methane was natural gas. And according to the European Space Agency, Egypt, especially in the area around the Nile River, emits a lot of methane. Exactly as I proposed in episode 125, the function of the step pyramid evolution for the extraction of bedrock deposits of methane gas. He then goes on to describe the pressure conditions and capabilities of the reaction chambers within the Red Pyramid, the primary subject for today's episode. Again, all of this coming directly from a PhD in both physics and mathematics. But that's not all. In his article from the Daily Plasma blog, engineer Andy Hall, contributor to the Electric Universe and Thunderbolts project, describes my hypothesis regarding megalithic chemistry, and I'll quote a few things here. First, Drum presents a thesis that the ancient structures were chemical processing plants used to produce chemicals for solution mining and crop fertilizer. How mundane, yet sensible. The ancients weren't communicating with aliens, spirits, stars, or the dead, but were actually making nitrates to fertilize their crops and acids to solution mine and process precious metals. Of course they were, just like we do and every other society one cares to look at throughout history. He backs his thesis with on-site investigations to confirm predicted channels, passages, chambers, and other features for fluid flow, pressure control, and containment in the Egyptian pyramid temple complexes. Trace elements from these processes are even identified. Furthermore, I believe, this is a quote from Andy Hall directly, that he is substantially, if not wholly, correct. In my former career, I built and operated cogeneration power plants integrated with a variety of chemical processes and visited too many refining, processing, and manufacturing plants to count. So Andy Hall is a qualified engineer who had a career building and operating cogeneration power plants that integrated a variety of chemical processes. And he resumes stating here, I know a process when I see one. Drum identifies precisely the use of chambers, passages, tunnels, and even the choice of rock used in a construction and how it integrates into an overall process flow. He identifies the chemistry, the process, and the system's integration, as well as the products and the purpose. The products and purpose make perfect sense in growing an agricultural empire, and the use cases justify the expense, unlike any other theory ever presented. The integrity of his work is in identifying how the pieces and parts worked together. They worked like chemical plants do today, mixing and reacting, settling and separating, transferring aqueous solutions here and there. The vessels they used were stone, not steel, but the processes were no different. He provides common sense, holistically viable, technically verifiable answers. This dramatically separates his from any other theory. He also correctly identifies the power source that ran the processes, nature's electricity, lightning, and telluric currents. This is another reason I know he's right. He's the only theorist who doesn't lose his mind and go extraterrestrial when it comes to the energy source. He understands it comes from the earth. No aliens were needed. Drum's examination is primarily of the Giza Plateau and its pyramid complex and certain standing stone sites in the UK and Europe, but I contend his model will apply throughout time and geography across most, if not all, megalithic sites, because it provides the simplest, most verifiable answer that fits with the needs and capabilities of those cultures. It's a theme repeated at every site one can consider a cradle of civilization. Occam's razor will prove Drum right. End quote. And if you haven't seen it yet, Andy also made a fantastic video breaking down the various hypotheses presented in my book and here on the channel entitled Megalithic Chemistry. that is now available on the Thunderbolts Project YouTube channel. And after a serendipitous series of events, Andy and I have finally gotten in touch, and you can anticipate some groundbreaking collaborations coming up soon. These are just two examples of the overwhelming support that I have received from qualified individuals from both the academic and professional fields, ranging from physics and chemistry to electrical engineers and petroleum geologists, and the list goes on. So Alexandre and Andy, from the bottom of my heart, thank you so much for your encouragement and support. And I'll put links to both articles and the video in the description below. So now, ladies and gentlemen, with that being said, let's turn up the pressure and the temperature inside the first chamber of the Red Pyramid, otherwise known as the primary steam reformer. And within this chamber, a reaction occurs between methane and water that produces hydrogen and carbon monoxide, as I explained in episode 156 by the following procedure. Step 1. Fill the chamber with water until the connecting shaft between the first two reformers has been filled. This isolates the space within the primary steam reformer and sets the initial pressure and temperature conditions within the chamber. Next, the methane fill process is initiated, and the methane gas, which is lighter than air, will flow into the chamber and rise into the upper reaction vault. This process continues until the reactor is filled with methane gas. Next, the water level inside of the chamber is increased further, compressing the methane gas into the upper reaction vault, gradually increasing both the pressure and temperature. This process continues, utilizing the water to compress the methane further into the reaction vault like a plunger or piston, pushing up on the gas, further increasing the temperature and pressure within the system. The water level is raised until it has reached the 7th tier in the reaction vault, and the reaction between the methane and water producing hydrogen and carbon monoxide will proceed, bringing us to this stage here, with the compressed hydrogen and carbon monoxide syngas in the upper vault of the first chamber. Now, before we get to the math, a quick announcement. My Brainstorm podcast with Ben and Finn is now available. Ben is a physicist, and Finn is a science author, and both are contributors to the Electric Universe and Thunderbolts Project. This is an absolutely fascinating conversation discussing a variety of aspects of my work, and my appearance on the Osiris Project channel also just premiered, featuring an in-depth analysis of the Userkov Pyramid with one of my colleagues and an original member of the Osiris Project who participated in their epic expeditions to Egypt from 2010 to 2013, whose chemical analysis data will be coming up later in this video. So please go check these out and subscribe, as I will be doing follow-up interviews on both channels, links in the video description below. All right, now, buckle your seatbelts, as the true capabilities of the Red Pyramid's reaction chambers are about to be revealed, with calculations showing the temperature and pressure conditions that can be achieved inside of the primary steam reformer. Starting here, with the total volume of the chamber, with the query, calculate the volume of the first chamber inside the Red Pyramid of Dashur. And you can see I've included the entire chain of information if you want to pause the video and read all of the details. So the total volume of the first chamber is estimated at 384 cubic meters. Next query. Okay, now, please calculate the volume of the upper 7 feet inside of this same chamber. And this upper 7 feet of this reaction chamber is a critical detail that I will be coming back to again soon during the episode focusing on the pump shaft and the external reservoir. All right, everyone, just a quick announcement. The first book in the Land of Chem series is now back in stock. This gorgeous Egyptian Blue second edition is the exact same text as the first print, but now featuring the new blue color design. Also, a brand new merch shop is up and running, featuring all of your favorite logos, tons of new color options, and my personal favorite, stickers. So whether you are sticking these to the bottom of your skateboard or plastering the walls of your office bathroom stalls, go grab some now and put them everywhere you can find a spot. All available at thelandofchem.com. Thank you all so much for the support. Now, back to the video. And we have the full volume calculations and considerations here, with the final answer estimated at 20.3 cubic meters for the upper 7 feet of the primary reaction chamber. Okay, now, so we have our initial volume, 384 cubic meters, and our final volume, 20.3 cubic meters, V1 and V2. All right, next query. Please calculate the temperature and pressure changes in the following adiabatic compression system with initial temperature 25 degrees Celsius, initial pressure 1 atmosphere, initial volume 384 cubic meters, final volume 20 cubic meters, and the gas is methane. So now, what happens to our starting temperature and pressure? I'll walk you through all of the calculations so you can see each figure step by step. Beginning here with initial temperature, T1, 298.15 Kelvin. Initial pressure, P1, 1 atmosphere. Initial volume, V1, 384 cubic meters. Final volume, V2, 20 cubic meters, with our gas, methane. So methane is a polyatomic gas with a specific heat ratio of approximately 1.31 at room temperature. Next, the adiabatic process equations. For an adiabatic process, the relationships between pressure, volume, and temperature are as follows. Next, our temperature and volume equation here, solving for the final temperature. So step 1, we will calculate our volume ratio with the initial volume and final volume giving us a ratio of 19.2. Step 2, calculate the final pressure using our specific heat ratio for methane of 1.31 and the calculations here with the final pressure P2 coming out to 47.963 atmospheres. 47 atmospheres final pressure. Step 3, calculate the final temperature T2, again using the specific heat ratio for methane of 1.31 with the calculations here. Temperature 2, final temperature coming out to 744.74 Kelvin. So our final answer for these adiabatic compression of methane calculations, final pressure approximately 47 atmospheres, and final temperature approximately 471 degrees Celsius or 744.7 degrees Kelvin. Now, let me read that one more time and let this sink in for just a minute. The final pressure achieved inside of the primary steam reformer of the Red Pyramid is almost 48 atmospheres. And the final temperature in that same chamber is 472 approximately degrees Celsius. Absolutely staggering. Next, I ran the same calculations again with a slightly higher starting temperature, as it can get pretty hot inside of these chambers on the average day, this time starting at 30 degrees Celsius, with a bit more compression, this time into the upper 19 cubic meters. So we have 5 degrees Celsius more starting temperature and 1 extra cubic meter of compression. Now what happens? Final answer, final temperature, 604 degrees Celsius and final pressure of 37 atmospheres. So in this scenario, we have slightly higher final temperature and slightly lower final pressure than the first calculations. So just for fun, I took the average of these two data sets and came up with a final reaction temperature of 538 degrees Celsius and a final reaction pressure of 42 atmospheres. 538 degrees Celsius and 42 atmospheres of pressure, which takes us once again Full circle. Back to episode 27, the function of the pyramid body, with one of the primary justifications for the massive core of stones surrounding the reaction chambers being the containment of the tremendous internal pressure within the system. Now, the next series of calculations. Query here: what reaction happens between water and methane at 538 degrees Celsius and 42 atmospheres? And I'll quote here: at 538 degrees Celsius and 42 atmospheres, the reaction between water and methane is most likely to proceed via steam reforming of methane, a well-known industrial process, with the reaction as follows, exactly as I've described: methane plus water equals carbon monoxide and hydrogen. The key points regarding the thermodynamics and catalysts stated here. The reaction is endothermic, favored by high temperatures like 538 degrees Celsius. High pressure, 42 atmospheres, shifts the equilibrium to the left, but the temperature is sufficient to drive the reaction forward if catalyzed. Regarding the catalysts, this reaction typically requires a catalyst to proceed at significant rates under these conditions. Well, it just so happens that these reactors are teeming with catalyst material, as you will see in just a moment. And a final note here regarding the practical context: these conditions are milder than the typical industrial steam reforming that occurs between 700 to 1,000 degrees Celsius at around 20 to 30 atmospheres, but still feasible for partial conversion, especially with a catalyst. But there is also something very special that happens to water under these same conditions that will also facilitate this reaction sequence. So what happens to water at 538 degrees Celsius and 42 atmospheres? At 538 C and 42 atmospheres, water is in a supercritical state. Water exists as a supercritical fluid, neither distinctly liquid nor gas, with unique properties like high density and high diffusivity. This state is often exploited in industrial applications like supercritical water oxidation or power generation. So what happens between water and methane at these same temperature and pressure conditions? At 538 degrees C and 42 atmospheres, water is in a supercritical state and methane is a supercritical fluid or gas-like state. Under these conditions, the reaction between water and methane is primarily governed by steam reforming. Again, the primary reaction being steam reforming of methane. The most likely reaction under these conditions that we have achieved within the first chamber of the red pyramid, the most likely reaction is steam reforming, where methane reacts with water or steam to produce carbon monoxide and hydrogen. Again, the thermodynamics: this reaction is endothermic and favored at high temperatures like 538 C. The equilibrium shifts towards the product of carbon monoxide and hydrogen due to the high temperature. The pressure effect: at 42 atmospheres, the increased pressure slightly disfavors the reaction because it produces more moles of gas. However, the high temperature dominates, still driving the reaction forward. And last but not least, regarding the supercritical water state, supercritical water enhances reaction rates due to its unique solvent properties, high diffusivity, and ability to dissolve organic compounds like methane, creating a homogeneous reaction environment. Ladies and gentlemen, the truth shall set you free. And I will quote one more time here: the expected outcome of these temperature and pressure conditions within the first chamber of the red pyramid. The primary products are carbon monoxide and hydrogen via steam reforming, with possible traces of carbon dioxide from the water-gas shift reaction. The exact product distribution depends on the methane to water ratio, the presence of catalysts, and residence time in the reaction environment, i.e., the longer it sits in the chamber, the more conversion of the products are achieved. The math speaks for itself. and the reaction chambers of the Red Pyramid have been precisely engineered to produce the exact temperature and pressure conditions to drive this reaction without exceeding operating temperatures that will damage the internal limestone blocks. This will be coming up again in part 3. But as always, ladies and gentlemen, this is just physics and chemistry 101. So what about the catalyst material that really pushes this reaction forward? And what if we were to introduce electric fields into this system? Let's start here. Scale-up studies on electrically driven steam methane reforming. This work is devoted to scale-up parametric studies of a new reactor system for the steam reforming of methane driven by electrical current. The main distinguishing feature of this type of reactor is the use of direct electrical current flowing through metal particles to heat the whole reactor volume. Well, it just so happens that we discovered 39 different types of metal particles inside the reaction chambers of the Red Pyramid, which also contains nickel, the main catalyst utilized in the methane steam reforming process. And I'll quote from this article here: improving nickel catalysts using electric fields, a DFT, an experimental study of the methane steam reforming reaction. This work demonstrates the benefits of applying an external electric field to the methane steam reforming reaction in order to tune the catalytic activity of nickel. Through combined DFT calculations and experimental work, we present evidence for the usefulness of an electric field in improving the efficiency of the current methane steam reforming process, specifically lowering the overall temperature requirements. So, by introducing electric fields and effective catalyst materials, the activation temperature of the methane steam reforming reaction can be decreased below the 700 to 1000 C of conventional reformers, temperatures that would not be sustainable within these limestone chambers. And remember from episode 108, electric fields inside the Great Pyramid, that the Egyptian pyramids are literally designed to concentrate both electric and magnetic fields. As revealed in this paper here, electromagnetic properties of the Great Pyramid, first multipole resonances, and energy concentration, showing the concentration of electric and magnetic fields surrounding the primary reaction chamber of the Great Pyramid. And in episode 117, I explained the roles of electric fields in driving chemical reactions. As best summarized in this article here, electric field intensified chemical processes and reaction chemistry. Stating here, electric fields represent an important resource that can be utilized for process intensification in the chemical industry. Utilization of electric fields provides an efficient and cost-effective way for intensified chemical processing and reaction chemistry. And it turns out that electric fields can also be applied to the methane steam reforming reaction. So remember that we have already achieved temperature and pressures within this reaction chamber that will produce the reaction between methane and water, creating hydrogen and carbon monoxide, with temperatures around 811 Kelvin. The addition of catalysts like nickel, which I have just shown are present inside of these chambers, and electric fields would just be icing on the cake to further increase the percentage of conversion, improving the efficacy of the reaction. So remember, we have 811 degrees Kelvin inside of the primary steam reformer chamber. Check this out. Support effects on catalysis of low temperature methane steam reforming. Stated here in the abstract, low temperature, less than 500 Kelvin methane steam reforming in an electric field was investigated over various catalysts. Catalysts which include cerium oxide. I'm sure you can already see where this is going. And this reaction can be achieved at less than 500 Kelvin, and we have 811 K plus catalyst. Next, this article here, low temperature hydrogen production by catalytic steam reforming of methane in an electric field. Stating here in the abstract, catalytic steam reforming of methane in an electric field, otherwise known as electroreforming, at low temperatures such as 423 K was investigated. 423 K methane steam reforming. And one more article here to really drive this reaction home, entitled Low Temperature Steam Reforming of Methane Over Metal Catalyst Supported on Cerium Zirconium Oxide in an Electric Field. Again, from the abstract here, catalytic steam reforming of methane in an electric field named electroreforming was conducted over metal catalysts supported on cerium oxide and cerium zirconium oxide at low temperatures such as 423 K, where conventional catalytic reactions hardly proceed. The conversion of methane was greatly increased by weak and effective application of an electric field to the catalyst bed. Oh, cerium and zirconium catalyst, you say? Don't tell me. That, of course, both cerium and zirconium were discovered in the chemical analysis data from the metal staining inside of the red pyramid. And I'll be coming back to the role of these electric fields and catalysts later when we reach the reactions within the final synthesis chamber and the low temperature strontium catalyzed ammonia synthesis reactions that were presented in episode 152. So now that I have shown that this reactor can achieve the temperature and pressure required to produce the methane steam reforming reaction, and that we have evidence of the exact type of catalyst that we use today, including nickel, cerium, and zirconium, let's take a look at how the reaction process moves into the secondary air reformer. So we concluded the last episode with our product syngas of hydrogen and carbon monoxide in the upper vault of the primary steam reformer. Now, at this stage of the reaction, there is also water in the northern pump shaft, and we'll be coming back to this later in a focused episode on this series. And you can see here, at the bottom of the secondary reformer on the south side of the chamber, this shaft. Another never fully excavated shaft that is now completely covered by the modern wood plank flooring inside of the chamber. This shaft is the drain shaft utilized in this series of steps. So here, I've added the drain shaft, and we will lower the water level inside of the chambers through this drain shaft that will first start pulling water from the secondary air reformer, dropping lower and lower, and will then drain water from the primary steam reformer. And as the water level in the primary steam reformer decreases, the gas will adhere to the surface of the water, aided by the high pressure within the chamber and surface adhesion between the gas and water. Remember, surface adhesion. Adhesion is the tendency of dissimilar particles or surfaces to cling to one another. And as the water continues to drain in this direction, moving south toward the drain, it will eventually drop below the level of the connecting shaft, creating an aperture between this high pressure system and this low pressure system, through which the gases can flow into the secondary air reformer. So we have three factors at play. First, surface adhesion between the gas and the water. Second, the south directional flow of the water moving from chamber 1 into chamber 2. And third, the pressure differential between the primary steam reformer and the secondary air reformer, all three of which will facilitate the movements of gases in a south direction, moving from chamber 1 into chamber 2, and the hydrogen and carbon monoxide, being lighter than air, will flow up, rising into the upper reaction vault of the secondary air reformer, leaving us at this stage here, with the hydrogen and carbon monoxide syngas in the upper reaction vault of the secondary air reformer. And before we conclude with today's episode, allow me to introduce Exhibit A. This image showing the southern wall of the primary steam reformer and the clear flow dynamics pattern indicating the movement of gases exactly as I just described, flowing from the upper vault of the primary steam reformer through the connecting shaft into the secondary air reformer. And as I said in part 1 of this series, the Red Pyramid is the smoking gun of this ancient pyramid chemical engineering technology, displaying not only evidence of the fluid dynamics of this manufacturing process, but demonstrating the physics and mathematical capabilities that are engineered into the tiered vaults of these chambers. These structures were designed to communicate exactly how they operated. By reducing volume, you increase temperature and pressure. And by a simple process of detailed examination, reverse engineering, and mathematical calculations, the bewildering temperature and pressure capabilities of this chemical reactor system have finally been revealed. The secondary air reformer. As in one of these holes, or rather housings, in the upper vault of the secondary air reformer, we discovered elevated concentrations of zinc and lead. And I'll show you the area where those samples were taken. You can see here in the secondary air reformer that there is a pattern of staining moving from the connecting shaft up into the vault of the reaction chamber. And again, at the 1, 2, 3rd tier, you can see the very clear delineation and change in the density of the reaction. You'll also notice that the color and the concentration of the staining is significantly higher in this chamber when compared to chamber number 1, indicating that there were higher temperatures and pressures involved in this stage of the reaction sequence. And we've done this before, but we'll go ahead and show you the UV light. Let me turn this off, and then I'll show you the staining under UV light. And I've presented the chemical composition analysis of the samples taken of this staining in a series entitled Red Pyramid Staining Chemical Analysis, Parts 1, 2, and 3. That shows the full breakdown and chemical analysis of the stains. And most significantly, we have iron, copper, zinc, antimony, lead, and then there's a vast array of other trace minerals and metals. including strontium. Now, all of these compounds, metals, and minerals found in the chemical composition analysis are naturally occurring in limestone. So there's nothing unusual about the presence of these materials. The question remains, what is causing the drip staining to form on the surface of the stone? Again, this is a process known as geological extrusion, where the stone has been heated to a high temperature and subjected to fluctuations of temperature and pressure, that causing the liquefied compounds to drip out of the metal. Looks pretty cool under UV light, and not much fluorescence. And if we were looking at organic compounds here, you would see a lot of fluorescence. And we'll do this again when we get to the vault of the secondary air reformer. All right, let me switch back to the flashlight. All right, so now back to the reaction dynamics. In the photos I showed at the beginning of the episode, you will see that this southern wall is completely covered in staining. Unfortunately, all of that is now obscured by the wooden staircase leading up to the final synthesis chamber. And you can see that these holes, or housings rather, are transverse, lateral housings. So let me step back here so you can see both of these bilateral housings. They're in the exact same place on each side of the secondary air reformer. And there's staining emanating from both of these. So again, the areas where you see the most significant drip staining are the areas where there were higher amounts of temperature and pressure. And below this wooden planking here, there is also another unexcavated pit here. That's the outlet shaft for the draining process that was used to remove water from the first two reaction chambers. So the hydrogen and carbon monoxide would have moved into this chamber along the surface of the water, draining out in this direction. The gases moving up into the upper vault of the chamber. The water level is raised again to isolate this reaction chamber. Water raised into the upper vault. So now we're talking chemistry 101. The increase of temperature and pressure by manipulating volume to facilitate these chemical reactions. However, these are not the only mechanisms of operation that were utilized to drive this reaction sequence. So now we're moving into the realm of advanced chemistry. involving oriented external electric fields and sound propagation that also facilitated the forward progress and momentum of the reaction and the direction of the reaction, pushing it through the structure. So in the first chamber, we have a high concentration of staining on the southwestern wall. And as we ascend the stairs here, we will see the exact same thing and more housings that I proposed in episode, hell, I don't remember what episode it is. Missing components from the Red Pyramid. That there was a one-way valve system that was once installed in the upper vault of this reaction chamber. And you can see the extremely dense concentration of staining here. So the hydrogen and carbon monoxide gases reacted with air inside of this chamber, hence the nomenclature secondary air reformer. The oxygen in the air reacts with the carbon monoxide to produce carbon dioxide. And then we have nitrogen and hydrogen remaining in the reaction vault. Are two synthesis gases from which the gaseous ammonia is produced. And you can see how dense and concentrated the staining is here in the upper reaction vault. Now, that carbon dioxide is soluble in water. So that carbon dioxide byproduct will dissolve into the water in the chamber and can then be removed by draining the chamber prior to the final synthesis stage. Again, I'm not going into all the details. I highly recommend checking out the playlist, The Red Pyramid, if you want a more thorough explanation of all of the chemical reactions and mechanisms of operation. So one thing here. All right, so this hole is where sample 59 was taken. That showed elevated concentrations of lead and zinc. And it was taken from this black drip staining. And the melting points of those two metals zinc is about 420, lead is about 325 Celsius. So let's say 400 C. Just so happens to be the exact same range that is utilized in the modern Haber process for the production of ammonia. And one thing I noticed in our previous visit, there's an accumulation of some unusual material in here. specifically in this hole over here. There's a huge clump. You can see it kind of here of black material in here. And it looks like that black drip staining is emanating from that black material. And as proposed in episode Missing Components from the Red Pyramid, I believe these bilateral housings once held the one-way valve mechanism that was installed in the upper vault of this secondary air reformer. So if you look here at the ceiling, you can see some drip staining at the very top flat surface of the upper vault, right here. Okay? If a bat is hanging upside down from that flat surface, how could it possibly produce that drip staining? It is physically impossible. Not to mention that we have chemical analysis that conclusively proves that this staining has absolutely nothing to do with bats, nor does the smell of ammonia. And I can very clearly smell here standing next to the entrance of the final synthesis chamber. All right, so now we're looking at the southwestern corner of the secondary air reformer, and look at how dense and concentrated the black staining is here. So again, we're looking at reaction dynamics, showing the flow and directionality of the reaction sequence as indicated by the pattern and density of the staining. So again, look at the concentration of the black staining near these holes, these housings. There's another bilateral series of holes here. And then there's this one here. And I'll add while I'm in here that every single one of these joints is sealed and mortared. It is a huge fallacy that the Egyptian pyramids are mortarless. And you can see there the sealer and the mortar in between these joints. These chambers are not only watertight, but also airtight. Still today, after thousands and thousands of years, you could fill this chamber with water. You can see my lovely wife Alexa down there. And it'd just be like a giant swimming pool. And so the concentration of the staining here in this area of the reaction chambers is pretty crazy looking. Again, it's much more dense on the southern sides of the chambers. Okay, so this is the southeastern corner. And let's compare this southeastern corner to the southwestern corner. Much more dense over here. So the reaction itself, and we're talking about sound propagation through these chambers now, again, advanced chemistry, moving away from simple compression of gases to increased temperature and pressure into additional mechanisms of operation that drive these reactions, specifically electric field chemistry. Before I forget, for any viewers that stayed tuned to the end of the video, it's a sticker. Again, you always find crazy shit when you're looking with the UV light. That looks crazy. Oh, we do have some green there. All right, good. And we'll keep this going so you can see a close-up of these bilateral housings here. Getting a good magenta glow there from some of this. That's pretty cool. There's some green in there. This one's a little harder to reach. There we go. Again, if you hit all of these walls, there's no telling what you would find. And you can't see that with the naked eye, but there's certainly some. Splooge right there. There's some interesting colors going on right here.
And the sequence that I am about to run was first presented in part 1 and 2 of this series in episode 156 and 157, along with mathematical calculations proving the temperature and pressure capabilities of these reaction chambers that produce the chemical conversion of methane gas and water into hydrogen and carbon monoxide within the primary steam reformer of the Red Pyramid. So if you are new to the channel and just joining for this episode, please go back and watch the first 2 installments so you can get caught up on what you are about to see. So now let's run the system to see where we concluded in last week's video. All right, now, so we have our hydrogen and carbon monoxide syngas in the upper vaulted chamber of the secondary aeroformer here, where the next stage of the reaction will proceed, with the hydrogen and carbon monoxide syngas and oxygen and nitrogen from the air reacting to produce hydrogen, nitrogen, water, and carbon dioxide. This mechanism of introducing air, which is already in the chamber, provides the nitrogen for the final ammonia synthesis and oxygen, which will allow the effective removal of the carbon monoxide by creating water-soluble carbon dioxide. So before we get to the reaction sequence illustrations, let's go back to establishing the case for these high temperature and pressure reactions that was mathematically proven in a series of calculations demonstrating capabilities of these chambers to produce conditions of 538 degrees Celsius and 42 atmospheres of pressure. And again, if you are new to the channel, it is absolutely critical to go back and watch part 1 and 2 of this series, episode 156 and 157. And remember, Exhibit A, this image showing the intense dark staining in the upper reaction vault and the gas flow dynamics moving from the primary steam reformer through the connecting shaft into the secondary aeroformer. So now, allow me to introduce a few more images from inside of the chambers of the Red Pyramid, as it is the smoking gun for evidence of this ancient Egyptian pyramid chemical engineering technology. So here we have Exhibit B, showing the dark, nebulous staining in the upper reaction vault of the primary steam reformer. This image showing the northern face of the chamber here. Next, Exhibit C, the southern wall of the primary steam reformer with even darker staining in the upper vault, direct evidence of these high temperature and pressure reaction conditions. And a few more images of the same area here, and magnified so you can really see up close the staining in the upper reaction vaults. And I'll be coming back to the staining and chemical analysis later in this series. Next, I pulled the original image of Exhibit A, the doctored version that was published by John Romer here on the left, and the original black and white frame on the right, clearly demonstrating the reaction dynamics of gases flowing from the upper reaction vault through the connecting shaft into the secondary aeroformer, exactly as I have previously described. Now, into the secondary aeroformer with Exhibit D, showing the exact same type of staining like we saw in the primary steam reformer, concentrated into the upper reaction vault, the area that experiences these high temperature and pressure conditions. And finally, Exhibit E, another old photo from inside of the secondary aeroformer, this one showing the southern wall. This area is now completely covered with the modern staircase that gives access into this connecting shaft toward the final synthesis chamber. And the drain shaft at the bottom of the secondary aeroformer is visible down here at the bottom. And I'll be showing in just a moment that the most intense staining in this entire system is concentrated up here on the southern side of the secondary aeroformer upper reaction vault leading into the connecting shaft. And there is a very specific reason for this that will now be revealed. So here is where we concluded episode 157 with the hydrogen and carbon monoxide in the upper vault of the secondary aeroformer. But for those of you that have been paying close attention, you may remember that there is something critical that we need to include in this diagram. So let's go back to episode 89, missing components from the Red Pyramid, and these bilateral housings on the 6th tier of the reaction vault that I have proposed may have been anchor points for a heat exchanger baffle system that allowed the unidirectional airflow of gases while reducing their temperature as they moved into the final synthesis chamber. And I also highlighted how every single diagram of the red pyramid has the configuration of these housings incorrect. There are not 3 on each side. There are only 2. And unless they have been completely covered to the point that they are absolutely indistinguishable, there are 0 housings in the primary steam reformer. Just go back and watch any of the Sunday site visit footage from my many visits inside the red pyramid so you can see it for yourself. And in episode 99, high temperature reactions inside the red pyramid, I showed this area, the upper southern side of the secondary air reformer, the area that displays the most intense and concentrated staining of the entire system. And sample number 59 taken from the black material from inside of one of the housings, and the elevated concentrations of lead and zinc, whose melting points are 372 degrees Celsius and 419 degrees Celsius, respectively, which perfectly fall in line with the temperature calculations from the previous episode showing operating temperatures around 500 degrees Celsius and still well within the operating temperatures that can be sustained by these limestone chambers. So back to our diagram here and this missing component, which after further research, I have concluded was most likely a pressure actuated check valve, the various configurations of which you can see here that allow unidirectional flow of fluid, either gases or liquids, once sufficient pressure has been reached to open the valve mechanism. And an interesting note here, frequently check valves are used for pressure control. A common application is to employ them as a relief valve to protect a heat exchanger. So this missing component may have been multifunctional in this area, functioning as both a heat exchanger and check valve. And here are a few examples of check valves, again, that allow flow in only one direction once sufficient pressure has been reached to open the valve mechanism. Pressure actuated check valves. So now let's install our check valve heat exchanger into the housings of the secondary air reformer and resume where we left off, now including the air in the chamber, providing the oxygen and nitrogen for the remainder of the reaction. And the system proceeds with the exact same mechanisms of operation that have been previously explained. All right, everyone, as I just mentioned, if you want to help support the channel and get access to some exclusive research content, check out the Land of Chem members-only channel now with a new tier called The Alchemists, featuring a 3-part episode revealing the function of the Teotihuacan Pyramid Complex. Also, a completely unscripted, unedited Ask Me Anything video every single month, now on part 5. And ladies and gentlemen, I can finally announce a brand new series entitled The Land of Chem in the Lab that will feature a variety of experiments designed to test the hypotheses presented here on the Land of Chem channel. Links to everything in the video description below. Thank you all so much for the support. Now, back to the video. All right, here we go. So we resume filling the chamber until the connecting shaft between the first 2 reactors has been filled, isolating the reaction space inside of the secondary air reformer and setting the initial temperature and pressure conditions. Continue raising the water level, compressing the reactants into the upper vault, gradually increasing the temperature and pressure until the reaction proceeds between the hydrogen, oxygen, and carbon monoxide that produces water and carbon dioxide, both of which are soluble in water that is filling the chamber. So under these conditions, the side products will dissolve into the water, leaving us with the hydrogen and nitrogen and our side product of dissolved carbon dioxide in the water here, which will now be eliminated from the system. And this is exactly what we do today to remove the carbon dioxide byproduct during the modern Haber process reactions, where water is introduced here to remove the soluble carbon dioxide, leaving the nitrogen and hydrogen synthesis gases for the next stage of the final reaction. So inside of the red pyramid, we drain out the water containing the dissolved carbon dioxide, eliminating the byproduct from the system. But we will see this carbon dioxide again, as it is another valuable chemical reactant for the next pyramid in the manufacturing sequence. So now that the carbon dioxide is gone, we refill the chambers again with fresh water, compressing the gas as high as it will possibly go into the reaction vault, raising the water 33 feet into the chamber. Again, remember the upper 7 feet from the last episode. This is as high as the water will rise in the system without activating the northern pump shaft that you can see here. And as these reactions have been running, this pump shaft has also been filling with water that is being pushed higher up the shaft due to the internal pressures. So we have an immense column of water here that will be very useful to drive these reactions, the full explanation of which will be coming in a focused episode on the external reservoir and northern pump shaft mechanisms. So we activate the pump shaft, enabling the water to be compressed even further into the system, increasing the pressure and opening the check valve, allowing both water, hydrogen, and nitrogen to flow into the final synthesis chamber. And as the pump compresses more water into the northern shaft, the water level will continue to rise, pushing the bubble of gases through the connecting shaft and into the final synthesis chamber. So now, let's run the full system so you can see the entire reaction sequence in action. Hell yeah, but we're not done yet. There are still 3 more parts to this series on the red pyramid, including the final synthesis chamber, the external reservoir and northern pump shaft, and the grand finale, the staining, catalysts, and electric fields. So if you haven't already, please subscribe and remember to click that little notification bell so you don't miss out on this week's Sunday site visit as we return to Dashur to investigate the reaction chambers of the red pyramid up close in person. Now to begin, in part 1, episode 156, the physics-based science of this ancient industrial-scale chemical engineering technology was first introduced by explaining the chemical conversion of methane into hydrogen and carbon monoxide within the primary steam reformer. Followed by part 2, episode 157, temperature and pressure capabilities of the red pyramid reactors, presenting mathematical calculations demonstrating the capacity of these chambers to produce temperatures above 500 degrees Celsius and more than 40 atmospheres of pressure. And in part 3, missing components, physics and chemistry of the secondary air reformer. The mechanisms of operation within the second chamber were elucidated, along with a revelation regarding the critical missing component that was first discussed back in episode 89, that was anchored into the bilateral housings in the upper vault of the secondary air reformer that were shown in last week's Sunday site visit. And if you haven't seen episode 158 yet, it is a must watch so that you can understand the function of this missing component and exactly how it was integrated into the chemical manufacturing sequence. I'll put links in the video description below, and all of these episodes have now been added to the Red Pyramid playlist. So thus far, we have converted methane into hydrogen and carbon monoxide in the primary steam reformer, then added air to introduce nitrogen, and transformed the carbon monoxide into water-soluble carbon dioxide, which was then removed from the system, leaving hydrogen and nitrogen, the final reactants that were pumped into the final synthesis chamber according to the following sequence. And if you are new to the channel, please go back and watch parts 1, 2, and 3 so that you can get caught up to where we are today. So now, let's turn on this ancient chemical engineering machine and run the process. So now we have the nitrogen and hydrogen in the upper vault of the final synthesis chamber, where the final conversion will create gaseous ammonia. Ammonia gas is highly soluble in water, meaning that it will easily dissolve into water even at room temperature and pressure. But first, let's examine the reaction between hydrogen and nitrogen that creates the ammonia gas. And whether you are an OG subscriber since day one or a new viewer, everything that is presented here on this channel is cumulative, with episode after episode building the foundations for subsequent research, planning and laying groundwork for videos like this when all of the pieces finally come together and the full puzzle picture is unveiled. So remember, back in episode 108, electric fields inside the Great Pyramid, when the concept of electric field concentration within the Egyptian pyramids was first introduced with this study, revealing that the Great Pyramid of Giza can focus electromagnetic energy, entitled Electromagnetic Properties of the Great Pyramid, First Multipole Resonances and Energy Concentration, which experimentally demonstrated that the Great Pyramid was designed to concentrate electric fields in the area surrounding the sulfur furnace and acoustic catalyst antechamber. And in episode 120, the Great Pyramid ultrasound catalyst, I explained how these concentrated electric fields were integrated into the operation of the Great Pyramid as a catalyst for the sonochemical reaction that created a dilute solution of sulfuric acid. To reiterate, the electric fields induced the inverse piezoelectric effect within the red granite components of the Great Pyramid to catalyze a series of chemical reactions producing the final sulfuric acid product. And I'll be coming back to the Great Pyramid later in this series once we finish with the red and bent pyramids of Dashur. And I propose that the same properties and capability of concentrating electric fields around the primary reaction chambers also applies to the reactors of the Red Pyramid. And in episode 117, Electric Field Chemistry, I presented several research papers detailing the roles of electric fields in facilitating and catalyzing chemical reactions. This one here, entitled Electric Field Mediated Chemistry, Uncovering and Exploiting the Potential of Oriented Electric Fields to Exert Chemical Catalysis and Reaction Control. Best summarized in this article, entitled Electric Field Intensified Chemical Processes and Reaction Chemistry, stating here, electric fields represent an important resource that can be utilized for process intensification in the chemical industry. Utilization of electric fields provides an efficient and cost-effective way for intensified chemical processing and reaction chemistry. But lo and behold, in episode 152, electric field facilitated low-temperature ammonia synthesis. It was experimentally proven that electric fields can be utilized in producing ammonia gas at low temperatures in multiple studies. The first one here, on the elucidation of the role of electric fields on low-temperature ammonia synthesis using isotopes, stating here, we have found that an electric field brings high yield on low temperature catalytic ammonia synthesis over a cesium, ruthenium, strontium, zirconium oxide catalyst. And here is a close-up of the process model illustrating the induced electric fields here over this strontium zirconium oxide catalyst that drives the low temperature creation of the final ammonia molecule. And again, here in this paper, entitled Electromagnetic Field Enables Ammonia Synthesis at Low Temperatures, stating here that using commercial iron-based catalysts, a university team devised an electromagnetic field-assisted Haber-Bosch method for ammonia synthesis under moderate circumstances. With the electromagnetic field aid, the onset temperature is 100 degrees Celsius, which is obviously lower than the onset temperature without EMF support of 300 degrees Celsius. Now, let me read that again one more time just to emphasize this point, as it will be relevant again in just a moment. They were able to synthesize ammonia under moderate circumstances with an onset temperature of 100 degrees Celsius, significantly lower than the conventional onset temperature of 300 degrees Celsius. This new EMF-assisted Haber-Bosch approach boosts ammonia yield 5 times while decreasing energy usage. With this model here, demonstrating the same process over a standard iron catalyst. And of course, the red pyramid is equipped with all of these catalyst materials as proven by the chemical analysis, which has been presented and discussed extensively here on the channel regarding the samples that were collected from the red staining throughout the system, which contain all of the catalyst materials that have been utilized in every stage of the reaction sequence thus far, starting with nickel in the primary steam reformer, iron, the primary catalyst used in the Haber-Bosch synthesis process, and the novel strontium zirconium catalyst that was implemented in the electric field catalyzed low temperature ammonia synthesis experiments. And in episode 142, lightning and fertilizer, I explained how the red pyramid was designed to capture lightning in a bottle by building a structure that could internalize and contain the same chemical reaction that occurs in the atmosphere during lightning strikes that creates water-soluble nitrogen fertilizers, literally making fertilizer out of air, which is exactly what we have been doing in the last 2 chambers of the red pyramid, where air is introduced into the system to provide nitrogen that is then converted via electric fields into ammonia gas within the final synthesis chamber. But instead of using steel pressure chambers like the one you can see here, a historical example of the final synthesis chamber utilized in the modern Haber process, they implemented chambers like this. Massive limestone structures embedded within the body of pyramids that were intentionally engineered to contain the immense pressure generated while the system was operational. So now, here we are inside of the final synthesis chamber. But what you can see here is not the original configuration of the chamber. This entire pit was excavated and the floor was removed in search for hidden passages, chambers, and pharaonic treasures, of which they found absolutely nothing. And you can see here the level of the floor, the bottom of the chamber, that would have originally looked something like this. And I propose that there was something in this chamber that must have provided the impetus and justification for the intensely laborious removal of all of this stone. They saw something in this chamber that gave them a reason to dig further. The ammonia solution extraction shaft, and they began destroying the floor as they followed the shaft further down into the structure. But after expending an enormous amount of work, they found nothing. The project was abandoned, and the pit is what we have left of that effort today. So now that we have established the location for the extraction shaft, let's turn this thing on and make some ammonia. And here's where we left off in last week's episode with the hydrogen and nitrogen in the upper vault of the final synthesis chamber. Next, the pump shaft is reactivated, compressing the remaining water in the northern pump shaft into the upper reaction vault, gradually increasing the temperature and pressure until the pump has reached the resting block at the bottom of the northern pump shaft. And for some of you that were paying close attention to last week's Sunday site visit, alarm bells and light bulbs should be going off right now, as I was extremely intentional to spend a good amount of time documenting and explaining the engineering behind the configuration of the resting block component at the bottom of the northern pump shaft. This mechanism of raising the water into the final synthesis chamber initiates the reaction between the nitrogen and hydrogen in the presence of electric fields and catalyst material coating the chamber that generates ammonia gas. And remember from these research papers that this can occur at initial temperatures as low as 100 degrees Celsius, which is actually ideal in this case, where lower temperatures and higher pressures are more suitable for the production of the aqueous ammonia solution. Recall from episode 156 that the major difference between the modern Haber process and this ancient chemical engineering system is that today we make liquid ammonia, ammonia gas cooled into a liquid, whereas the ancient technology created aqueous ammonia solutions, gas dissolved into water. And as I stated before, ammonia gas is highly soluble in water, and it will easily dissolve into the water in the chamber, even under ambient temperatures and pressures. So the gas will begin to dissolve into the water. And this removal of the ammonia gas by dissolution prevents the reverse reaction of ammonia breakdown and also facilitates the forward momentum of the remaining hydrogen and nitrogen reaction that produces more ammonia gas. So as the process continues, more ammonia dissolves into the water under pressure, creating the final product, aqueous ammonia solution, as you can see here. Then the extraction shaft is opened, and the product can be quickly removed from the system, preventing any reaction between the product solution and the limestone reactor walls. Generally speaking, any reaction between a dilute aqueous ammonia solution and the limestone would be negligible, if anything at all, especially at low temperatures as described, and if it is removed immediately as shown here. Now keep in mind, these slides are simply demonstrating the mechanisms of operation in each chamber individually. The whole system will be put together as a continuous manufacturing sequence in an upcoming video. So now, let's see the chambers in operation from start to finish. So there you have it, ladies and gentlemen, the function of the final synthesis chamber and the electric field catalyzed low temperature aqueous ammonia synthesis reaction. But that's not all. We still need to examine the function of the northern pump shaft, including some mathematical calculations and the external reservoir. And last but not least, the grand finale: lightning, electric fields,
and catalysts. So if you haven't already, please subscribe, as I will be doing this exact same process with all of the major pyramids, including the Bent Pyramid, the Great Pyramid, the Central Pyramid, and the Final Pyramid later on in this series, involving a meticulous examination of the mechanisms of operation driving the ancient Egyptian pyramid, chemical engineering technology. In part one of this series, the chemical reaction sequence and mechanisms of operation within the primary steam reformer of the Red Pyramid were presented, followed by part two, a series of mathematical calculations demonstrating the immense temperature and pressure capabilities within these reactors that were enabled through the sophisticated physics-based engineering design. And in part three, we moved into the secondary air reformer, revealing the function of the missing component that was once housed in the upper vault of this chamber. And in part four, the transformation of hydrogen and nitrogen into the aqueous ammonia product solution within the final synthesis chamber was completed. And this series of chemical reactions that began with methane were initiated in the primary steam reformer, moving into the secondary air reformer, and last through the final synthesis chamber, according to the sequence that you are about to see. And if you are new to the channel, all of these episodes are now available in the Red Pyramid playlist, link in the video description below, so you can get caught up on the following sequence. Now, let's turn on this chemical engineering system and watch the reaction chambers of the Red Pyramid come to life. All right, now let's go way back in the Land of Chem Vault to an episode from 3 years ago entitled The Egyptian Pyramid Pump Shafts, when I introduced an essential term that was discussed in a previous Sunday site visit as we explored the methane extraction and production facility at the Step Pyramid Complex in Saqqara. A chemical manufacturing process unit, as defined and elaborated upon here. So a chemical manufacturing process unit means the equipment assembled and connected by pipes or ducts to process raw materials and to manufacture an intended product. Sound familiar? A chemical manufacturing process unit consists of more than one unit operation. For the purpose of this subpart, chemical manufacturing process unit includes air oxidation reactors and their associated product separators and recovery devices, reactors and their associated product separators and recovery devices, distillation units and their associated distillate receivers and recovery devices, associated unit operations, associated recovery devices, and any feed, intermediate and product storage vessels, product transfer racks, and connected ducts and piping. A chemical manufacturing process unit includes pumps, compressors, agitators, pressure relief devices, sampling connection systems, open-ended valves or lines, valves, connectors, instrumentation systems, and control devices or systems. A chemical manufacturing process unit is identified by its primary product. So, of course, we have the series of 3 internal reaction chambers within the Red Pyramid that are linked to each other via connecting shafts, i.e. pipes or ducts. But there are several more functional components of this system that we still need to discuss. First, the external reservoir that surrounds the pyramid, and the northern pump shaft.
both of which are found in all of the Egyptian pyramids that were constructed after the step pyramid and are fundamental mechanisms of operation driving this ancient chemical engineering technology. Now, the configuration of the Red Pyramid's Eastern Temple is one of the least documented structural components due to the extent of later quarrying and general state of ruin. As you have seen in many previous Sunday site visits, there is almost nothing left of this temple as stated here. So far, archaeology has been unable to unearth any buildings within the pyramid complex other than a small temple on the eastern side, similar to the ones at Seneferu's two other pyramids. It is too small to be a true mortuary temple, so it probably served as a quote-unquote offering chapel. We've heard this terminology before. There is no sign of a proper mortuary temple or cult pyramids or any other tombs. The pyramid complex itself was originally surrounded by a perimeter wall made of limestone blocks, of which traces still remain, but most of its stones, and presumably those of the other elements in the complex, have likely been stolen and reused elsewhere. However, as I've previously proposed, the height of the external reservoir, as mentioned here, is estimated at 10 meters. So the enclosure wall surrounding the Red Pyramid at Dashur is not as well preserved or documented as that of the Great Pyramid, and precise measurements of its original height are scarce due to the current state of ruin. However, based on archaeological evidence and comparisons with similar structures from the Old Kingdom, such as the enclosure wall at the Pyramid of Djoser, otherwise known as the Step Pyramid, the Red Pyramid's enclosure wall is estimated to have been approximately 10 to 11 meters, approximately 33 feet tall. And as always, the measurements of these various process units encode important information, and the height of this external reservoir and its water level are directly connected and correspond to what will happen on the inside of the structure within the reaction chambers. And this reservoir system was supplied with purified water, as explained in episode 86, revealing the function of the great enclosure Giza El Mudir as a water treatment plant whose massive dimensions, as stated here, measure approximately 650 by 350 meters, and its walls were a massive 15 meters wide at their base. The walls have been excavated to a height of 15 meters, but their width suggests that they were originally much higher than this, which enabled the production of a staggering 3,412,500 cubic meters of treated water per cycle, which is more than 900 million gallons. So now, let's examine how this process unit operated, and we'll evaluate a few different diagrams, all of which include a speculative configuration of the design for this Eastern Temple. But we know for sure that there is a component connected directly into the exterior of the pyramid on the eastern side, as you can see noted here. Now, let's start with this side view, looking at the pyramid internal structure facing west. And we'll add the external reservoir here to the height of 10 meters or 33 feet, which, as I mentioned in previous episodes, the height of the first two reaction chambers is 12 meters or 40 feet, a difference of 7 feet between the height of the external reservoir and the height of the internal reaction chambers. And now, the reservoir is filled with water. Now, from a top-down perspective, with the reservoir now filled with water and introduced into the structure through the eastern pump inlet housing, and a different view here, showing a bit different speculative configuration of the inlet pump housing system, now filled with water, pumping water into the reaction chamber system via the shaft that connects into the bottom of the northern pump shaft that I've shown in several on-site expeditions. And now filling the chambers, and thus the northern pump shaft with water. Now, let's evaluate the system from the internal perspective so you can really see what's going on and the magic of the northern pump shaft in action, which acts as a counterweight pressure mechanism to drive the water within the reaction chambers higher into the vault. So we begin to introduce water into the system and raise the water level inside of the chambers until the connecting shaft between the first two reactors has been filled. And if you want more information about what is happening inside of these chambers, please refer to the previous episodes in this series, as today I am just focusing on the reservoir and the northern pump shaft. Now, as the pressure begins to increase within the reaction chambers, this will drive water up into the northern pump shaft, initiating a balancing act between the pressure inside of the chambers and the weight of the water column and pressure from the northern shaft, with the internal pressure pushing more water back up into the northern pump shaft, thus increasing the weight and counter pressure, which forces water to rise further up in the chambers. This will continue back and forth as more water is pumped in through the external reservoir inlet shaft, with the height of the water in the column forcing the water level to rise in the chambers, and the internal pressure within the chambers forcing the water to rise in the northern pump shaft until we have reached a point of complete equilibrium, where the water level in the chambers cannot go any higher and the water has completely filled the northern pump shaft, and no more water can be introduced into this system at this point without water shooting out of the top of the pump shaft. So now let's take another look from the outside perspective. So here we have the external reservoir filling the internal reaction chamber system, with the pressure from the internal forces and the water column in the northern pump shaft alternating back and forth, driving the water level up into both components until an equilibrium has been established here, where the height of the water inside of the chambers has reached 10 feet, the same level as the height of the water in the external reservoir, and the internal pressure from the reaction chambers has pushed the column of water back up the northern pump, completely filling the shaft. So, what happens now? Well, what you have just seen regarding the utilization of an external reservoir as both a source of water for the internal chemical reactions and as a mechanism of operation that drives the system is an ancient technological implementation of a water-filled enclosure system that far predates the construction of the Egyptian pyramids, as found in structures like Silbury Hill, where the external reservoir was utilized to facilitate that exothermic heat-generating reaction sequence, as explained in episode 106, Lightning, the Power Source of the Egyptian Pyramids, Part 1, and also in structures like Avebury and Stonehenge, as revealed in episode 115, The Function of Stonehenge. And as this technology evolved, it progressed from earthen enclosures dug into the bedrock into huge reservoirs erected around the Egyptian pyramids. And this component was integrated into and applies to all of the Egyptian pyramid chemical engineering structures, including the Bent Pyramid, the Great Pyramid, regarding the function of the subterranean pump system, as presented in episode 51, Great Pyramid Private Access into the Subterranean Chamber, and even the Central Pyramid, with this exceptional diagram here showing the height of the external reservoir, with all of these systems operating the same way, introducing water into the reaction chambers to drive the internal operations, as recently discussed in episode 139, hydrochloric acid and the central pyramid. So what happens inside of the red pyramid once this equilibrium has been reached? We have to have a mechanism to push the water from this column into the final chamber and raise it even higher. And that is where the northern pump comes into play. Now, the northern pump shaft itself is a valuable mechanism of this technology, providing us with 66 cubic meters of water, as shown in the calculations here. And at the bottom of the northern pump shaft, there is a message from the pyramid builders that tells us exactly what was happening in this system. Remember, I have suggested that there is communication encoded in the design of these structures, with every detail being meticulously engineered for a specific purpose. So remember this stop block from Sunday Site Visit 103. We'll take a look at this diagram showing the placement of the stones in the wall in this lowest section of the pump shaft and the configuration of this stone. It is showing you exactly what this system was engineered to do, which is allow the pump mechanism to come to rest at the bottom of the shaft, landing precisely on this angled stop block. This stone here, embedded into the wall of the shaft, is communicating through intentional engineering design the function of the northern pump shaft system. More on this coming up in part 6. So please subscribe and stay tuned.
All right, everyone, that is it for today's video. This was episode 171, Secrets of the Red Pyramid Exposed, Full Function Finally Revealed. I really hope you enjoyed today's video, and please remember to subscribe to the Land of Chem here on YouTube if you're interested in the technology of an ancient civilization utilizing physics and chemistry and the function of the Egyptian pyramids and other ancient structures from around the world. Click that little notification bell so you don't miss out on new episodes. Like, comment, share, and stay tuned. If you want to help support the channel and get access to exclusive research content, check out the Land of Chem members only channel and thelandofchem.com if you want to pick up a copy of the book or grab some merch. Links in the video description below. If you want to follow me on Instagram or on X, my handle is @thelandofchem. Also, don't forget, after you finish watching this video, please go subscribe to our 3 other channels. My wife Alexa's channel, Archeo Alchemy, our mutual channel, Let's Go with Lex and G, and the best channel on YouTube, Egyptian Trash Cat. For all you cat lovers out there, ladies and gentlemen, as always, thank you all so much for the support. I think that's it for today's episode. I will see you. Next time. Yo, are you still watching this? Please subscribe to the Land of Chem here on YouTube and click that little notification button. New videos coming out every single week. And check out this other episode. Come on, do it. Do it now.